So our first speaker of this last session is Léonard Monsaingeon from the University of Texas at Austin and Instituto Superior Técnico Lisbon. That's what's written here.
I'm
right?
actually from Lisbon, not from Austin.
Well, okay. Superior Técnico Lisbon.
Yes, I am.
Okay, and the title is New Optimal Transport Distance Between Non-Negative Radon Measures.
Okay. So before I start talking, there's three things I would like to do. The first one is to, of course, thank the organizers for giving me the great opportunity to be here today. The second one is to acknowledge my co-authors, so Stanislav Kondratiev and Dmitry Vorotnikov, who, despite their Russian-sounding names, are actually working in Coimbra University in Portugal. And the third thing I would like to do is tell you a little story, just to illustrate how fast the field is moving. So the timeline is as follows. We submitted the paper about a month and a half ago, and within the last month, we heard that two teams were completely independently working on exactly the same thing, and actually constructed exactly the same distance. The first team is composed of Liero, Milko, and Savare, who don't have a preprint yet, so fortunately we're the first ones. And the second team was Gabriel Perez's team from University of, right now I don't remember, a French university in Paris, Paris-Dauphine. My apologies. Something else I should specify is that I'm going to talk about non-negative finite radon measures. So just for simplicity, whenever you hear a measure, just think of finite non-negative radon measure. It will make things easier. So let me start by giving you just a one-slide crash course in optimal transportation, actually very partial reminders. So P2 here denotes the set of probability measures, so mass 1 with finite second moments. And whenever you give me two measures, rho 0 and rho 1, so probability measures, you can define the so-called quadratic Wasserstein distance, W2. The upper 2 stands for squared here, as follows. So assume you're asked to transport a measure here, say rho 0 of x, and you're asked to transport it in a somehow optimal way to rho 1 of y. So here the infimization is taken over gammas. I'm not going into the details because my time is very limited, but think of gammas, the small gammas over which I'm minimizing as all the possible ways to transport rho 0 to rho 1. And you should think of d gamma of x, y as the infinitesimal amount of mass that you're actually sending from, say, a given point x from the source measure to a target point y in the target measure. And there's a cost for this. The cost here would be simply the squared distance, Euclidean distance. So what you do is just you minimize over all possible ways to do that. Each time you give me an admissible transference plan, gamma, there's a cost. And when you minimize the cost over all possible transference plans, you obtain a distance, actually a squared distance here. There's actually many other formulations. There's a Monge, this is the Kantorovich formulation. There's also a Monge formulation in terms of transports. I mean, the whole theory is really fascinating, but I don't have time enough. But all of these are basically static problems. Here, all that matters to compute this distance is basically where each mass, each point from x here is transported to y, but there's no continuous evolution. You have no idea how a particle is actually moved from x to y. It's completely static. Turns out that there is a very nice dynamical representation of the squared Wasserstein distance, which is the so-called Benamou-Brenier formulation, or formula actually, going back to about 15 years ago, which is as follows. So you want to look at all the possible curves of measures, rho t. So now there's time. Let me, for simplicity, restrict to time evolving from 0 to 1. And you want to look at all possible vector fields and curves rho t, solving the continuity equation here. Every time you give me, say, a velocity field and a curve satisfying the continuity equation, there's a physical quantity associated, which is very natural, which is here the kinetic energy. You just integrate v squared times d rho and think of d rho as the mass. Right? Velocity squared times mass is indeed a kinetic energy. And the theorem is that if you look at all the possible curves and velocity fields that actually match the given points rho 0 and rho 1 at time 0 and 1, then you infimize over all possible velocity fields and curves, satisfying the continuity equation, then you obtain exactly the squared Wasserstein distance. So now you see it very clear. There is a dynamical evolution. You see time, and you see exactly how particles are transferred from row 0 to row 1. All the things that I'm going to talk about just after came from actually a very simple observation, which is the divergence form of this equation. So on the right-hand side, you have 0. And this has two very important consequences. The first one is that the PDE is mass conservative. And indeed here, the rho t, or probability measures for any time. All the intermediate measures, rho t, or stay with fixed mass 1. This is the first consequence. The second important consequence is, again, because of the divergence form, you can show that for every fixed time t, the optimal velocity field is actually potential. So you write just Vt equals gradient of P. Actually, the pressure function P is usually a quadratic convex function, which has very deep connections with Monge-Ampère equations, and so on and so on. But the field, the optimal field, is always potential. So now the goal for us was, well, here you have restriction on the mass. You have to compute distance between two measures, but two measures with the same mass normalized to 1, say. But now we want to somehow allow for mass variations. So here's the theorem definition. So M plus sub B, again, is for non-negative bounded or finite Radon measures. And here is the idea. So I'm going to define a new distance between any two measures. Again, rho 0 and rho 1 could have completely different masses, as follows. So instead of putting 0 on the right-hand side, you want to look at non-conservative continuity equations, NCC. So I'm just plugging in brute force on the right-hand side and putting a reaction term. And then, exactly in the same way as before, I have somehow naturally defined energy, which is this one. So every time you give me a potential ut, right, you still have the kinetic contribution, which is corresponding here to the squared velocity in the advection term, and you have also a price to pay for the reaction. And the reaction is penalized as this one. So there's a cost. And again, you want to infimize over all possible ways of transporting rho 0 to rho 1 according to the non-conservative continuity equation. So this is for the definition. This is what I called d squared. So this is the squared of my distance. And the theorem is that d is indeed a distance between non-negative finite Radon measures. Maybe a few comments or remarks, or in order at this stage. The first one is that due to the presence of rho multiplying everything on the reaction term, at least formally it's clear that there is a minimum principle, meaning that if you start from rho 0 non-negative and you let time evolve, for every t, rho t should stay non-negative. The second one is, of course, because I'm adding a reaction term. Reaction term is a reaction, so mass varies along the evolution. And this is precisely what allows me to compute the distance between two measures with possibly different masses. The second observation is that here, contrarily to the classical Wasserstein setting, I'm not requiring any decay at infinity. In the previous slide, the P sub 2 was standing for probability measures with finite second moments, which is a weak characterization of decay at infinity in some sense. Here, I'm not imposing any such condition. The third and maybe more important remark is that now I have possibly two different strategies. If I want to move masses around, well, obviously, because of this advection term, I can always kind of transport infinitesimal particles. But now, because I have an additional reaction term, I can also create or kill masses. And maybe to better illustrate this, let me borrow an image from Alexander Milko, which is the following. Assume I'm living currently in a city A, and I have to move to a city B because I get a new job. So what I do is just pack my stuff, rent a car, put all my stuff in the car and truck, actually, and start driving, right? So classical transport would be just, well, I'm only allowed to drive, and I have to find the optimal way, the optimal path, right? But now I can also actually, if you think of it, it's very natural. Maybe sometimes if you move out in a very far away city, it's more convenient to actually get rid of all your stuff, move, and then buy new stuff at the arrival, right? And actually you can do that simultaneously. While you're moving, you're just maybe just throwing stuff away and buying new stuff on the way, right? So this is basically the idea. And the consequence of this third remark is that the geometry of the metric space that we obtain is somehow related but also quite different from the classical geometry in the Wasserstein space. So unfortunately, I do not have time to speak about this, but this can be looked at, saying, by looking at two direct masses. What is the optimal way with my distance of transporting one direct mass at a position x0 to another position at distance x1? it turns out that at short range, basically it's Wasserstein. At long range, it's completely different. So just let me summarize by saying that the geometry is intrinsically different. So here's basically the main results that we were able to obtain about our distance. So the first theorem is a topological theorem. The second one is a more geometrical theorem. So the first set of results tells you that, so indeed, the set of measures endowed with this distance is a complete metric space. Of course, completeness is a very desirable property if you want to do analysis on metric spaces, for example. And the distance d is sequentially equivalent to the bounded Lipschitz distance, which I do not have time to define, but the bounded Lipschitz distance is somehow a classical distance between measures. The second result that we obtain is that our distance d is lower semi-continuous with respect to the weak star conversions of measures and metrizes the narrow conversions. Just a word about the narrow conversions. The bounded Lipschitz distance here is well known to metrize narrow conversions. So if I'm telling you that my distance is sequentially equivalent to bounded Lipschitz, then of course our distance also metrizes weak star conversions, narrow conversions. The third result somehow relates our distance and the classical Wasserstein distance, because now our distance is defined on any kind of measures, right? So when you restrict it, you give me two probability measures, I can compute both the Wasserstein distance, but also our distance. And it turns out that our distance is always less or equal to the Wasserstein distance, which means that somehow the topology of our metric space is weaker than the topology of the Wasserstein spaces. The fourth result is that compactly supported measures are dense with respect to our measure. And more precisely, the result is as follows. You give me any measure rho, you restrict it to a big ball, BR, and then you send R to infinity. Then the distance between the restriction of the measure and the initial measure tends to 0 when the radius of the big ball grows to infinity. So this is for the topological properties of our distance. Let me speak very shortly about the geometrical properties of our distance. Yes?
Your measure set finite mass.
Finite masses, yes. Yeah. So the first geometrical result is as follows. So now that we have a metric space, just give me a L Lipschitz curve. Lipschitz, of course, with respect to our distance. Then I can always find the potential, U, such that the non-conservative continuity equation is satisfied, and the weighted H1 norm of U is actually less than L for almost every time. This weighted H1 norm of U is just this quantity. This is the squared H1 norm, right? So this norm is less than the Lipschitz constant for almost every t. The second geometrical result is that our metric space is actually more than just a length space, but it's actually a geodesic space, meaning that for any two endpoints, rho 0, rho 1, you can always find a minimizer in the definition, whoops, here. The inf is always a mean. You can always find a curve of measures that has constant speed in the metric sense, that the distance between rho t and rho s is t minus s times the distance between the two endpoints. And moreover, this minimum is actually attained for a constant speed curve, meaning that the potential u that you want to use to represent the geodesic is actually constant in the H1 norm. So maybe just a quick comment. All of these properties are actually very classical for the Wasserstein setting, right? One of the major points here is that in the Wasserstein setting, you are restricted to unit masses, and you have control of the tightness, because you impose second moments, finite second moments. So you have somehow decay at infinity. Here, I don't have any of these two things. So somehow we have to work out the details, technically speaking. For example, the fact that compactly supported measures are dense somehow helps us retrieving some compactness, okay? The lower semi-continuity with respect to weak star is also a key ingredient in the proof, for example, of the existence of geodesics. You just want to look at a minimizing sequence and get enough compactness to pass to the limit. This is exactly how we do it, but we just use the weak star conversions as an intermediate thing. So now that we have a geodesic space, I'm going to define somehow a Riemannian formalism a la Otto. So Otto did this, exactly what I'm going to do here in the classical setting of Wasserstein spaces. Think of here, we have now a representation of geodesics, right? And you know that in general, in a manifold, what is the tangent space? The tangent space is just a set of all time derivatives of curves, of C1 curves, say, in a manifold. But now, if I'm restricting to representation of curves through these non-conservative continuity equations, I know that the time derivative of a curve is uniquely somehow identified to a term of this form, which in turn gives you a unique potential u. So I'm just defining by hand the tangent plane at a point rho to my manifold as follows. So it's just the set of all possible zetas being represented through this elliptic equation. So somehow I have a 1-1 correspondence between potentials u in H1 of d rho, rho being the base points in my manifold, and tangent vectors. And you can actually do much more than this. You can define the Riemannian matrix, which is just basically the weighted H1 of d rho scalar product. And it turns out that this is the nice point of view to view M, so the set of non-negative finite Radon measures, as a manifold endowed with this somehow formal Riemannian structure. One of the huge advantages of doing so is that once you have a Riemannian formalism, you can compute differentials. And the matrix, the Riemannian matrix, allows you to pull back differentials of real-valued functionals to tangent vectors, formally through the chain rule. Okay? And there's a very easy back-of-the-envelope computation showing you that if you gave me a functional f on the space of measures, then this is exactly how you compute gradients. For those of you who know the Otto's formalism, it's very similar. So it's just 2 minutes, right? Perfect. Okay, so now I know how to compute gradients, and let me give you, this is the last slide, don't worry, a very somehow nice application of this theory. So let me consider the following reaction diffusion problem, which actually arises from population dynamics theory. So assume that you're working in a bounded set omega, and that at each point x, you have a prescribed quantity of resources, m of x, and you want to compute the evolution of the density of animals, say, rho of tx. Then what animals tend to do is that they tend to reproduce according to this rate. So here, if you have more resources than animals, it's actually favorable, so animals tend to reproduce, and vice versa. If you have more animal than resources, they tend to die, because they don't have enough food, right? So this is just the reaction term, and here, this advection term basically encodes the fact that animals want to move to the most favorable environment. So they move along the gradient of the fitness, which is just the difference between how much resource you have and how much animals there are around you. Well, now if you remember my formula for computing the gradients, it turns out that this PDE here can be interpreted, at least formally, as a gradient flow of this energy functional with respect to our Wasserstein type matrix. And what we're able to obtain is the following. So for any initial datum rho 0 that you give me, you can show conversions exponentially fast to the least energy solution. Here, the least energy solution being obviously m of x, the steady state, right? And this was already known by a paper by Kostner and Winkler, but somehow by very abstract comparison theorems, and so they had no explicit rates whatsoever, just comparison principles. Here, because we identified a variational structure, we gained some insights, and as a byproduct, we retrieve explicit convergence rates. Just one very last observation, I know my time is out. We do not have lambda displacement convexity, so we had to find way around. And this is why my exponent here, my exponential gamma rate, depends actually on the initial datum. But we can track explicitly the dependence. And this is all I wanted to tell you. So thank you.
Any questions?